Geometric deep learning is a framework to study different kind of data domains for which deep learning can be models can be developed and studied under one common framework. So I'll be starting with graphs, and I'll have a recap of the deep learning that is done on the grids and how we generalize on graphs. And my lecture in the first and second session will be mostly focused on graph and graph neural networks. And after which Professor Michael Bronstein, during the afternoon first session, he'll try to now broadly present this geometric deep learning framework. And finally, in the last two sessions, there will be two very advanced deep learning models that will be discussed by Christian and Fabrizio. So the outline of presentation for this session will be, first, I'll recap on the convolution, on the grids basically, then how we can generalize on graph data sets resulting in graph convolution. Finally, next it will be message passing for graph neural networks, which becomes the main underlying framework behind GNN models. It will be followed by several graph learning tasks that we can do on graph data sets. Then I'll discuss attention and how attention is related to graph neural networks and what transformers can be developed for graph data sets. And finally, I'll conclude with what are the takeaway messages for the session today. So let me start with the convolution. In the last decade, deep learning has been successful on data sets that have regular spatial structure. These are such as images, text, and speech. So if we look at the way the images and the text and speech are structured, they are grid-like structure data sets. So this is an example of an image. If we zoom out a particular patch of the image, it will consist of a grid of pixels, and at each pixel there will be a vector that represents the color value of the particular pixels. So this is arranged in a 2D fashion or 3D fashion if you consider this pixel value as well, in a grid-like fashion. So this is a regular image data set. Text and speech are also in the similar fashion. They are one-dimensional grids, and at each time step, a particular word is arranged, and for each word, a feature vector is present. So these are the data structures on which deep learning has been very successful in the last decade. And before we move on to convolution, how could we perform deep learning on this, and what are the problems that we would encounter if there was no any prior geometric information that is encoded into the architecture? So for example, let's consider image, which is one of the grid structure data sets. So if we consider image, and if we apply perceptrons on this image, the problem that we have that it has to learn the shift invariance from the data. What does this mean? If we take the image and apply a perceptron, we have to flatten the input image pixels into a vector, and we lose the structure, the spatial orientation of the pixels in the image. So now we have x1, which represents the image. It's a series, it's a vector of pixels, and we pass on to the perceptron. There can be multiple layers after this. The y1 can be passed again to the next layer. Then it becomes a multi-layer perceptron. So it gives the output y1. It has the parameters w and b. So if we shift this image of cat slightly on the left, we have a completely different feature vector at the input. And it does not, although both the objects are the same, the feature vectors, the input vectors x1 and x2 are not the same. It changes because of the shift in the original image. And this leads to an output y2. So if we don't have any notion of this prior information of the image, that it can it still represents the same object even we shift the actual object in the image. If we don't have any way to encode this information in the architecture, the model, which is the perceptron here, has to learn this invariance due to shift from the data itself. So if we want y1 and y2 to be same, we have to train on all different possible or many possible shifts of the images that we have for this object. And this is what it means that the model has to learn shift invariance from the data. So is there an architecture that is equivariant or invariant to the shift of the data? Yes, the convolution neural networks. So the convolution performed on the images makes the output of the convolution equivariant to the shift. The shift is also referred to as translation in an interchangeable manner. And finally, after a series of convolution and pooling, in the final layer, if we perform global pooling, it provides shift invariance finally. So whatever shift we perform during the previous or during the intermediate layers of convolution, finally a global pooling will provide shift invariance. So let me show you this more clearly now. I think there was the convolution would have already been covered in the previous session in the last week. So this maybe can serve as a recap to the lessons in the last week. So this architecture, which is LENET, is a classical CNN architecture by Jan LeCun, and this consists of a series of convolution, pooling, and finally global pooling followed by a classifier layer. So at each of the convolution here, uh, a filter is applied on patches of the input image to generate output pixels for the next layer. This operator can be represented by this equation, where the multiplication of the filter matrix with the input image is shown. And if we consider, for example, this image, and these are the pixel values, consider that. So when this filter is applied on a patch of input image, for this position, the corresponding output is presented or computed here. Now, if we shift this image to the right, for example, this output would also be shifted to the right. So this is what the equivariance means. The convolution operation is equivariance to the shift of the image in the input. And so this is this convolution. It presents the output equivalent to the shift, and it precisely means this, that when we are shifting the input image, the abstract features that are learned as a output of the convolution, this should also be shifted. So one idea of understanding this concept is using this image and its corresponding output abstract features. So, and finally, when we apply a global invariant function at the end, which does the pooling, it enables shifted invariance, because on the images, if we are doing, for example, segmentation task, we don't want this global pooling, because the final output, we want it to be equivalent to the input, because of the fact that when we are doing the shift at the image, the same translation should also be reflected on the output. It should not be distorted in some sense. So, and when we are trying to predict the label for the entire image, we want the global pooling at the end, so that for both these two images, which are two different images but kind of have the same object, we want the same class. So this in turn help achieve that. So as a summary of what CNN does is, first, it has this encoded as an inductive bias into the architecture, the shift invariance and equivariance, and the filter matrix, the filter kernels, they enable local receptive fields. So this is important for the robustness of the network, because when we experience certain noises in the images, because of the local reception field, they are not propagated globally, and the network is hence robust to certain noises or perturbation in the image. Then it has shared parameters. One filter weight can be used and convolved over different patches of the image. It helps to detect stationary patterns that may be present at multiple regions in the image. Next, the hierarchical nature of the network allows the composition of multiple scalar features. So these are the good characteristics. Now, in terms of the complexity, the parameters that are present with the filters, they're not dependent on the input size. So if there's a model pre-trained weights that was trained on maybe 100 cross 100, it can be applied to 1000 cross 1000 in principle and also in practice. And the convolution operation has linear complexity with the input size, which is ON. So these are the good characteristics of CNNs that can be understood to be providing the good performance that CNNs have witnessed in the last few years. So now we would want to generalize these good characteristics onto graphs, because there are several graph structure datasets and a wide availability that is present for graphs. So we'll now move on and try to understand what are graphs and how to generalize all these good characteristics of convolution from images and grids to the graph structure datasets. So what are graphs? If you think, graphs are data structures which represent irregular connectivity structure in the data set. So for example, if you consider molecules, if you consider transportation maps, these come with certain underlying structure. So a particular a nitrogen atom in this graph is connected to C and C, and this is a structure that we would like to use in the model. So formally, what is a graph? It's a collection of it's a tuple that represents the collection of vertices, the collection of edges, and I mean, if we try to represent this it becomes an adjacency matrix. So how a graph works, or how a graph is represented, we have a collection of objects. So a collection of objects in this case would be atoms. In this case would be certain points in the transportation map. So these are the collection of objects. They're treated as nodes. And there is an underlying relation which can have any irregular form. Any node can have any number of neighbors. Any node can be connected to any other nodes of the graph, or there may be no connection between two nodes as well. For example, these two don't have a connection. So these kind of irregular relations or edges are present, and these relations are called edges. So this is the structure of the graph. Now each node of the graph may have an attribute, may have certain information. Each edge on the graph may have certain information. So how would you understand this in the perspective of this? The edge information could represent whether the edge is a single bond or whether it's a double bond. The node information may represent whether the node is a nitrogen atom or carbon atom or oxygen atom, and so on. And there may be optionally a global attribute of the graph which represents the certain information related to the entire graph as a whole. For example, certain energy related to this molecule, etc. So this becomes a formal definition or representation of the graph, and the edges can be used. The edges can be represented using an adjacency matrix as shown here. There are actually several areas where graphs are present in abundance. I presented here a snapshot of certain domains. I'll quickly walk through each of them to have an understanding of what kind of domains are present and how the data sets can be obtained in the form of graphs. In chemistry, like I discussed earlier, we have molecular graphs, and we can use these molecular graphs to learn the chemical properties and also predict for future tasks. Ultimately, it can be used to kind of repurpose or redesign drugs and other applications also in the field of molecular chemistry. In social networks, there are very big graphs of social connectivity of users, and the interactions among the users are multidimensional. So graph neural networks or deep learning for graphs can be developed for ultimate commercial and social applications. In physics, several labs perform simulations and experiments of particles. The particles can be represented as nodes, and the interaction can be represented as the edges. And when deep learning models can kind of model these dynamics, it helps accelerate physics research and perform experiments that would otherwise take hours or months or years of experiments by kind of doing the same thing in an experimental setting. In transportation, the transportation are inherently a graph structure data set. So deep learning can be applied there to learn from traffic behavior and understand the dynamics of the networks to kind of help the ultimate management of transport, and also predict time estimates for users, end users. In neuroscience, these data sets, the brain regions are represented as graph data sets where the connectivity represents the connection of how different brain regions interact with each other. So deep learning can be used on these kind of graphs to help understand different aspects of certain neurodiseases. And finally, combinatorial optimization. So different combinatorial optimization problems are represented as graphs, and deep learning can be used there to develop better approximated solution for difficult problems in combinatorial optimization. So I think this provides a snapshot of several real-world applications where we have data sets in the form of graphs, and this motivates the development of deep learning for graph data sets which have irregular structure. On images and text, we have certain regular structure, and we have designated neural networks for that. But we have a lot of data sets in present real world scenario where data sets can be represented in the form of graphs, and therefore the motivation behind this today's tutorial and the graph neural network as a whole is to also extend deep learning and develop very powerful applications for these kind of applications and domain areas. So since the representation of the graph structure can be used with an agency matrix, let me briefly highlight some of the quick concepts. So in this case, the edges are undirected, meaning they don't have a direction. If there's an edge between 1 and 0, it naturally means that 0 is connected to 1 and 1 is connected to 0, and so on for all the other nodes. So in such a case of undirected graph, the adjacency matrix would be symmetric. So if you perform a transpose on the A, we would still have the same matrix. And you can see actually the lower triangular half of this matrix is similar to the upper triangular matrix in a sense that it mirrors the lower triangular matrix. So now if we try to permute the try to change the ordering of the nodes. So initially it was 0, 1, 2, 3, 4, and 5. So if I try to have a random change of ordering, so I'll do 1, 2, 3, 5, 0, and 4. So I changed the ordering of the nodes, because of which the adjacency matrix got changed. You can see on the right. But both the graphs and both the adjacency matrix represents the same graph, right? So try to kind of relate it with the shift we had for the images. If we are trying to shift the object in the image, it would still represent the same image or the same object. Similarly, if we have a different ordering of the nodes and a different adjacency matrix as the result, even if the adjacency matrix are different, these two adjacency matrix represents the same graph, and there can be actually n factorial possible in ordering of the nodes, and as a result, the similar number of adjacency matrix. So now we have a problem. We have a situation that we want to encounter this. We want to account for this kind of nature of the geometric information that we have in the graph structure, that any kind of model we have must be permutation, equivariant, and invariant. So before going on to graph neural networks, let's try to apply MLPs on these graph data sets. So if we have if there was an image here and we applied MLPs, we got rid of the information of the spatial orientation of the pixels. In the same case, if we apply multi-layer perceptrons, we have to flatten out the node features. We get rid of the useful structure information that was in the present of a form of edges. And we have a node ordering. We have a feature vector corresponding to the node ordering. And when we pass to the perceptron, we have a certain output. If we change the node ordering, we would have a different feature vector altogether, and we would get a different output value y2. So now see that both these two graphs are the same, but only the indexing we are doing is different, and there are n factorial possibilities of indexing. So if we are using a multi-layer perceptron, there are two problems. First, we are losing the structure information that is present in the form of this connectivity edges, and second, we are also the model is also not able to learn the invariance due to the permutation of the nodes. So for these two feature vector, which both represent the same graph, we are having different outputs. So if we want to both these outputs to be the same prediction by the model, we would have to have all n factorial possible ordering of the graph and its corresponding feature vectors, input feature vectors, if we want the model to learn permutation invariance. So consider if we have like a million data samples and each node has an average of, let's say, 100 nodes. So we would have million times 100 factorial million times 100 factorial graphs, which we have to process through an MLP. So that becomes computationally very infeasible. So, and also the model has to learn the permutation invariance in the data. So because of this problem, we move towards an architecture that encodes this invariance due to the permutation in the architecture. And before moving, note that compared to the images in the graphs, we don't have any notion of the direction up, down, left, or right, as we had for the images or for the sequence. Similarly, in the images, each pixel would have a left, right, up, and down. So 4 neighborhood pixel each node would have, each node pixel would have in the image. But in case of graphs, each node have different number of neighbors. So note that these are the two key differences from the grids to the graphs. Now, if we try to focus on the convolution that was done in the graphs, this operator defines the convolution on images and grids that was done in the previous slides. This is defined in the spatial domain. In the spectral domain, we can also define the convolution, and it becomes an inverse Fourier transform of the multiplication pointers product of Fourier transform of the filter function and the input feature function. So this is because from the convolution theorem, the Fourier transform of the convolution of two functions is the pointwise product of the Fourier transforms. So this is precisely because of this theorem, we help understand, or we help come to this equation, which is the convolution in the spectral domain. Now we need to generalize both these definitions from images to graphs. For images, they are already defined and they have already been used since several years. For graphs, there's a need to define that because we want to generalize all those interesting and good properties that convolution had for images. The extension of one, which is the spatial convolution definition, is not straightforward, because remember that the filter matrix here considered a fixed node ordering. So if you recall the convolution being done on the image, the filter matrix and the image matrix, the ordering, there was a correspondence. So if a filter matrix in the kernel was a filter value was on the left top corner, it got multiplied with only the left top corner of the image patch that was selected. So and that's how also it considers this spatial ordering when this spatial convolution is applied to the images. So it's not very straightforward, but still we can generalize. I'll come to that part later. But let's try to generalize the convolution using spectral domain, in the spectral domain using this spectral convolution function. To generalize the spectral convolution on the graphs, we need two key backgrounds, the graph Laplacian and the eigen decomposition. So I'll try to define both of these so that in the next slide, we can understand that we use these operators when we are trying to define convolution for graphs. So the first operator is the graph Laplacian. So the graph Laplacian is essentially a function of the adjacency matrix. Adjacency matrix, as we saw earlier, if we include the identity matrix and D, which is the diagonal degree matrix, and have this term, it gives the graph Laplacian. So as an interpretation, if we take a graph and we have a consideration of central node being this red and its neighbors are denoted by yellow, then if we try to take the Laplacian of the information at a particular node here, it provides the difference of the information at this central node and the average value of the neighbors. So this is what the graph Laplacian says. It's kind of a difference of a central node information with the average of its neighbor node information. And this Laplacian can be decomposed by eigen decomposition to obtain Fourier function, which are the Laplacian eigenvectors. So the eigenvector matrix has a number of eigenvectors from 1 to n, and the eigenvalues is a diagonal matrix which has the eigenvalues from 1 to n corresponding to each of the eigenvectors. So these things are used for when we define the spectral graph convolution, because from the convolution theorem, we have this particular step, which is the convolution of a weight function and the input function. So when we apply the Fourier transform to the input h, for the graph we have this. We arise at this thing. We multiply with the eigenvector transpose to the input, and similarly in the weight filter matrix also we have a phi transpose times WL. So this is the equation that we arrive, and this becomes the vanilla spectral graph convolution. So it's basically a weight spectra filter and the input information in the spectral domain, and finally a phi is multiplied to get the output back in the spatial domain. So the phi here is for the inverse Fourier transform. The W hat is basically the Fourier of the W, which is this, and the phi transpose HL is the Fourier of the HL. So by this definition, we arise to a spectral convolution definition, and this was the first spectral graph convolution that was proposed in 2015. There was an attempt to generalize the convolution in the spectral domain on graphs. So if we have this kind of definition of a graph convolution, we have several limitations. First, these are computationally expensive because we have dense n square matrices, and we are doing eigen decomposition, which involves a cubic complexity. Similarly, the spectral filter which we have here is dependent on the eigen values. So we have O to the n parameters per layer, and hence, because of the presence of this n, the filter parameters number depends on the input size. So this is a very critical limitation, because remember that in convolution on the images, we have no dependency of the filter numbers on the input. So if we have a filter of, let's say, a 3 by 3, it can be applied to 100 cross 100 as well, and 1000 cross 1000 images as well. The filter size, the parameter size is not dependent on the input, but in this convolution, it is dependent on the input. And because of this dependency, the filters do not generalize across graphs. And finally, understand that when we're doing the convolution on the images, it had a local receptive field, and with the spectral graph convolution defined as such, there's no guarantee of any spatial localization. And the spatial localization is a very useful property that powers the good performance of GNNs. At the same time, it makes the model robust. So this is the first architecture, the spectral graph conv, but we'll see how we develop and get rid of the limitation in the following slides. So because this step considers eigen decomposition, this can be simplified into the above this equation, where is the filter value, the filter matrix, and on the graph Laplacian multiplied to the input. So this filter can be parameterized using a Chebyshev polynomial, and this is a ChebNet, which is a very interesting model that gets rid of several limitations that was brought by the previous model. So ChebNet, basically, what it does is it converts this spectral filter into a series of into a Chebyshev polynomial, in which we can define from the 0th to the a certain number of k steps, and the summation can be used to actually give the output of the graph convolution. So when this is considered, it basically is doing a k power of Laplacian. So this xk is defined with the scale Laplacian times the x of k minus 1 and k minus 2, which are respectively at the input, it's the feature vector, and the first x1 will be the Laplacian applied to that, and then this Laplacian is basically of a scale Laplacian. So it's for understanding, you can see it's just a Laplacian. So when we are trying to have this form, and if we have, let's say, k3 or 2, so we are having a multiplication of this Laplacian, and because the kth power of Laplacian is taken, the feature that it tries to encode, it becomes exactly k localized. So in the first hop, in the first step, the first one hop neighbor information is aggregated, and in the next step, if the k is higher, the next hop information is aggregated. So contrary to the spectral graph convolution that was defined earlier, which had no guarantee of localization, this ChebNet is exactly k localized. So let's see what are the properties and how it gets rid of some limitations of the previous convolution layer. So the first is, it is computationally linear because it doesn't have any eigen decomposition explicitly. So if you see this step, the filter was dependent on the n number of eigenvalues. So because we don't have this step and we no longer require eigen decomposition, we can simply perform convolution using this part, which was parameterized using the Chebyshev polynomial. So we get rid of the dependency on the input size, and we have a filter which has a constant number of parameters per each layer. So hence we have this very interesting property, which is the similar as the convolution for images. It becomes computationally linear, and we don't require eigen decomposition. So then we get rid of we improve the complexity, and the filter are no longer attached to eigenvectors of the graph. So hence they can generalize across different graphs as well. And one note about this is it still has no direction of no notion of direction, because this filter matrix would apply to each of the direction in the similar fashion, so that it is being termed as isotropic. This can be termed as isotropic filters. So so finally we come to a model ChebNet, which has this convolution filter, which it was derived from parameterizing a spectral filter, but because it doesn't use any spectral eigen decomposition or does multiplication in the spectral domain, it effectively becomes a spatial convolution. Spatial convolution in this respect, because we are not doing any more the computation in the spatial domain as it was done for the previous this part, where the convolution was being done in the spectral domain, and it was again multiplied with the eigenvector matrix to get it back to the spatial domain. So we're not doing any this kind of operation in this, and we are having a spatial convolution. So this ChebNet gets rid of certain limitations and becomes a very nice model that performs graph convolution, and it does in the spatial domain. We'll try to move ahead and try to simplify this. And first of all, like if we see the spatial convolution that was defined on graphs, it has this this form. And we also saw that we cannot straightforward generalize these for images, because this filter is considering a fixed node ordering, and which we don't have for graphs. So one simple solution for this is we can use the same W for each of the nodes that are the neighbors. So if this WJL is replaced by simply W of L, so now there is no any corresponding with the node ordering, we remove the J, then we have a spatial graph convolution. It's a very simple generalization. So it gets rid of the problem of this. Now there's we don't have to consider any fixed ordering, because if a node has a 5 number of neighbors, then the same W is applied to all the 5 neighbors information. So it's also an isotropic filter because there's no notion of direction. And when this is being applied, the first hop neighbors are considered. So it allows the local receptivity, and the parameters are independent again on the graph size. We can have a constant number of parameters and which are not dependent on the input size. And finally, we have weight sharing, because the weights, this same function is applied with the weight WL is applied to each of the nodes. So we have weight sharing. So these are the very good properties that we have when we generalize the spatial convolution to graphs. So this becomes a very basic, it's not very powerful, but it's a basic, and from here we start building on very good graph neural network models that are being used in recent times. So before moving ahead, I'll try to formalize what are permutation invariance and equivariance from whatever I discussed earlier. So if we have a function f, which is a GNN model, for example, we want to learn for a node feature matrix, which is H and A. H will be, the dimension of H will be n cross D. D is the feature dimension, n is the number of nodes. And the adjacency matrix A represents the connectivity structure, which is n cross n. So for a graph network, these two are the inputs. And if we want some output respect to the graph, which is permutation invariant, it basically means that when a permutation is applied to H and also the adjacency matrix, we should have the same output, no matter whatever permutation matrix is applied. For the case of equivariance, when we apply the permutation matrix on the node feature input and the adjacency matrix, the output should also be permuted, because if you consider similar to the semantic segmentation in the case of pixels in images, if you consider predicting some information on the nodes, for example, if there's a social media graph and the user A has certain output to be predicted, if the index of the user A changes and the user A is indexed somewhere, is permuted, the output should be retained for user A, because we are doing some node level prediction. So then in such case, we want permutation equivariant outputs. So this is the condition that represents the permutation equivariance. And we want our function or each graph convolution to be permutation equivariant, and how a general recipe of a GNN is constructed. It's being done by this this function here. So for each of the nodes from 1 to n, a permutation invariant function G helps aggregate the neighbor information. So this GCN, the vanilla graph convolution that was present in the earlier slide, it becomes a permutation invariant and local function that is applied to each of the nodes. So hence it becomes so whatever ordering of the neighbor is present, it still gives the same output when it's doing the neighborhood aggregation. So it's a local function, and when it is performed for all of the nodes, we get the permutation equivariance. So now if the node and the node 1 and the node n are, for example, interchanged, the output rows will be interchanged, because this will go at the bottom and the bottom will come to the top. So this enables the permutation equivariance. And finally, we have this f of h of a, which becomes a permutation equivalent function. And this is precisely the GNN that we have. So this the function, when applied to one node, is a permutation invariant, and when it's being applied for all different nodes, we have a GNN that takes in the input of all the nodes and output feature vector corresponding to each of the node. So this becomes the key recipe of GNN design, and you can see that each of the functions that are GNN equations, they can all be abstracted using this building example. So we move towards a graph convolution neural network, which is one of the very popular baselines that are used. So if I try to recall from one of the previous slide, if we represent the graph convolution neural network in the matrix form, we have a h of L and h to the power L and WL. That provides the output of n cross t for the next layer, which is the feature representation for all the n number of nodes in the graph. So if we have a vanilla GCN, basically when we are, if we are having a vanilla GCN, we are basically adding a degree normalization term, which means if 5 neighbors are aggregated, it takes the average information of all the 5 nodes. So it's represented by the 1 over degree. And it's basically taking the mean over all the incoming messages. So this becomes a vanilla GCN layer. And when we apply a nonlinear activation, we have the final vanilla GCN layer. So if we understand from the terms of a building block, this is simply taking all the neighbor information and taking the average of the neighbors, passing it to a weight function and nonlinear activation, and we have a feature update for the next layer. So this is very simple. It's very easy to understand. This becomes a vanilla graph convolution network. And the actual GCN model that was used in the paper contained the normalization that used the degree of both the source and the destination. So only this small part is changed, and it's still the kind of the notion or the concept of the GCN is still the same, in the sense that it's taking the summation, taking the average or normalization of all the neighbor information that are coming for a particular node. So this becomes the GCN model, and it's used very popularly as one of the very simplest baseline. And we'll try to understand about this also later, and in also the next session, like what are the theoretical implications of having this kind of layer. So we now have come to a stage where we started from convolution on images. We saw what are the challenges when we try to generalize on graphs, and then we developed graph convolution both in the spectral domain and the spatial domain. So now we'll try to understand the same architecture from a different perspective of message passing. And when we understand message passing, it becomes a core mechanism on which all different and mostly all of the GNNs are built on this message passing mechanism. So a deep graph neural network, or simply a graph neural network, consists of this pipeline. At the input, node features, edge features, and graph features are taken. At each layer, these features are updated. And at the final layer, the prediction layer, the final layer features are considered and passed to the classifier for the predictions. So where is the message passing? It's there at each of the GNN layers. So why it's called message passing? Because for each feature update of a node, we are trying to aggregate neighborhood information and then only update the node features. So for example, if we consider this graph, the node 3, if we want to update the feature presentation of node 3 from layer L to layer L plus 1, we consider, or based on the GCN equation that we had before, it takes in the information from node 4 and node 2, and then updates the feature information of node 3 to the next layer from the red to the green color. So this essentially is a message passing, because neighborhood messages are being sent to the destination, which leads to the updation of the node features. And the GCN equation that was present in the earlier, it's basically doing the same thing. I mean, when we have this equation, all the J nodes are passing messages for the update of feature representation of the I node. So this is one way to see the same GCN equation from the perspective of message passing, and it can be represented, or it can be abstracted in the more general way using this equation, which says that we have a function that has certain parameters. In this case, it's a W. It takes the input node features and the neighbor features, and it's a multi-set of neighbor information. There also can be some aggregation function. For example, in this case, it's a summation followed by degree normalization. So this equation represents a message passing based graph neural network. And how we can design a F, it's a very open area of research. And in the last 2-3 years, there have been several recipes, several models that tries to propose a function update F and the different aggregation matrices. So I'll try to show some of the very popular message passing based GNNs. And in the GCN, we saw that we are simply doing the neighborhood averaging of the information that is coming from the neighbor nodes to update the feature of the I. So in graph sage, it also used to concatenate the central node information when it was taking the average information of the neighbors. That was the main difference from GCN to graph sage. And they showed better performance, and also it looks very natural that a central node information concatenated with the neighbor information would provide a boost to the performance. In the graph stage, there were also some other aspects such as sampling of the neighbors, but that's skipped for this discussion. And also the second thing is that the aggregation function also had several choices. For example, the max aggregation function or other aggregation function were also to be used. In the gene layer, which is a more expressive than these two and more powerful than these two models, the aggregation function was changed to sum, and instead of concatenation, this output coming from the central node information I and the neighbors J was actually performed a summation instead of concatenation. And after that, when the filter parameters are multiplied, it uses a MLP instead of a simple filter matrix. So these are 3 examples. We also have several other sophisticated designs of the function F. So in all of these different block designs of different GNN layers, the idea is to use the HI and the multi-set of HJ and give the output HI. And this entire architecture inside is what that is representing the F. It has different components such as weight matrices to learn, nonlinear activation functions, and these are some attention weights that can be computed. So I won't go into details of these one by one, but I'm just showing that all these architectures have one thing in common, that they can be represented by this equation, and at the core of this equation we have the message passing, and it's also convolution, because that's how we came at the definition of the GCN. We saw in the previous, like the conception arrival of how GCN is constructed. So trying to change this function or trying to use different aggregation, different activation function is what leads to the discovery of new architecture, and also trying to improve, for example, in this case, this is a graph attention network layer. In this case, the source information and the destination information of a particular edge is used and passed through an attention mechanism, and finally the softmax attention scores are used when the neighbor information is aggregated for the next the feature update. So these kind of concepts can also be used to design the F function, and it's still a very active area of research. Now, what you can ask which one is the best model. I mean, in several cases, like we start always with the simple baselines, for example, a GCN or any of the other models as well, because these are all isotropic. They don't have any notion of directions when features are updated. And at other times, like when we're trying to have very sophisticated models, we perform some experiments by using different models and see like which performs better, and then try to study what led to the better performance. So that was about message passing and different GNN model designs. Now, what kind of different learning tasks that are performed on graph structure data sets? So here we talk about the final prediction layer that gives an idea of the graph learning tasks. So when after L number of GNN layers are computed, the respective feature outputs, in the final layer, the outputs can be passed into a classifier that is composed using MLP. So if we're doing to do any prediction, the prediction can be performed at 3 levels: the node levels, the graph level, and the edge level. So if we are going to do a node level prediction, we simply pass the final layer node information to classify MLP, and we obtain the node prediction. So it's done using this. If I want to predict something for the node 3, I'll pass the final layer information to an MLP and perform node prediction. These are basic stuff, like similar to what how convolution is doing, but I'm just showing that to kind of understand like how or what kind of graph learning tasks that are done on GNNs. So if we consider, for example, a social media graph, this node could represent a user. So if a property is to be predicted for the user, this final layer information of the particular user 3 is passed to MLP classifier, and then it predicts the nodes. Similarly, for edges, we can predict, for example, some information corresponding to the edges, and we simply can pass the source and destination information of the final layer, and then we have edge prediction. We can do simply for the graph level task as well. So this is how, like at the node level, edge level, and graph level, at all the 3 levels, prediction can be done. And it's not necessary that all 3 prediction will be done at the same time. If you're trying to, for example, predict a property of the molecular graph as a whole, we do graph level prediction. If you want to predict the property of a user in a social media graph, we do node level prediction, and so on. So this is how graph learning tasks can be done. So now, so far we have seen convolution, its generalization to graphs, the message passing GNNs, and different graph learning tasks that can be performed. Now I'll try to give a relation of GNNs with attention and how graph transformers can be developed. So I think in the last week, you may have already gone through the session of transformers in the NLP. So I'll show that transformers becomes a special case of graphs, and the attention mechanism becomes a special case of message passing. So how is this the case? Yeah. So if you see the attention and from using the attention mechanism, I would like to update the feature representation of a word transformer. It would basically receive messages from all other words in the sentence. So it's, in other words, it's doing message passing from all other words in the sentence to obtain a feature word representation for a particular word. So if we see and relate with the message passing that was done in GNNs, it's a similar thing, but the difference is in GNNs, the message passing is being done from the local neighbors. And with respect to the question, like what is a central node and what is the neighbor information, the node we consider is a central node. So at this point, we're considering this node, and the feature that is, the neighbor that is with respect to a central node, these are 3 nodes, this one, this node, and this is the third node. So these are the neighbors with respect to the central node. If we're trying to have this as a central node, it has one neighbor, which is this. So the central node is just a consideration. I mean, it applies to all. When we are doing GNN, it updates feature of all the nodes. So at each point, each node is a central node, and each node has a certain information coming from its neighbors. And the number of neighbors, the neighbors actually can also differ. So attention in transformers can be seen as a case of message passing, in a sense that in attention, the transformers, in attention of transformers, the message passing is done with all the words, whereas in GNNs, the message passing is done only with the local neighbors. So what is the equation that does this attention? I'm sure you must have already gone through in the last week during the transformers lecture, but I'll present this in the sense of a message passing GNN, which basically becomes a node update equation, which takes in all the other words in that sentence by multiplying with the attention scores. So this becomes the attention mechanism that is used to update the feature representation of a node I. So because attention is very powerful and it has been shown to be state of the art in several NLP applications, and it's a universal neural network architecture for handling sequential data sets. And in the recent time also, it's being applied to several other domains, such as for images, we have the vision transformers and so on. So the natural question is how we can generalize the transformers to graphs and have a unified architecture, because we now have clear connections from transformers and graph neural networks, because it both relies on the message passing mechanism. So the question is how to extend the graph transformers to graph structure datasets. How to extend the transformers to graph structure datasets. This is a question that we tackle in one of the works, and we developed graph transformer in 2020. So one obvious idea for having transformers to graph, you could say that it's already a graph transformer, because if we are applying on graph structure dataset, let's just apply to the local neighbors, and we have a graph transformer. So this is already there. In 2018, there was this very popular graph attention networks. Even today, it's used as one of the widely used graph attention or GNN baselines for different graph structure applications. So in GATS, the idea was to perform attention only to local neighbors, and it actually it showed a good performance compared to the architectures that time. But if we see now, there are open questions such as if we should use local attention or global attention, and that means that if we should use the sparse structure of the graph, or we should resort to the full graph structure as it is done in the case of sentences, and what are the positioning coding candidates to consider, and also the questions on scalability and pre-training. So in this work, generalization of transformers to graphs, we try to address some of these questions, and we have a baseline graph transformer developed as a result. So we consider two key design aspects. The first key design aspect is the sparsity. In case of NLP transformers, because an attention is performed for a particular word, it performed to all other words in the sentence, it becomes a fully connected graph of words. And why this fully connected graph makes sense? Because first, it's very difficult to find a meaningful sparse structure between different words in a sentence. So if this is a sentence, we don't know how this and transformer is related, or how the words this and is related. And we don't know how many words are related for a particular word in consideration. So we have an absence of a sparse structure in the graph, in the sentence graph. Similarly, if we consider sentences, they're usually less than tens or less than hundreds of nodes. So if we consider a fully connected graph, it's possible to fit into the memory. So if we have 100 a number of words in the sentence, we can simply have a 100 cross 100 graph. But in case of graphs which have arbitrary connectivity structure, the graph data sets, full attention is not feasible, because actually graphs can have millions or billions of nodes as well. So for NLP, it's possible. For actual real world graph data sets, it may not be possible. And when we're using the full graph structure, in case of real world graph data sets that have a structure present from its availability, we may be losing a very critical information. For example, if this node has 3 neighbors, it means that this node has certain critical information. So if this graph would be representing a team in an organization, it would show that maybe this node is more likely the boss of the group or the leader of the group, and as compared to this node, which only has 1 neighbor. So this person may be a subordinate working under a person this. So this information, how we are able to kind of infer, we are able to infer only because of the connectivity structure that is present. And hence it becomes a good inductive bias for training and generalization. And this rich information will be ignored if we simply connect each node to each of the other nodes, which is done in the NLP in case of sentences. So these are the two factors why when we try to generalize transformers on graphs, we consider the sparse connectivity structure. And second, the positional encoding. In NLP, in the original transformers, if we simply consider attention, it becomes a permutation invariant function as symbol to the GNNs. And if we have this, basically we are transforming the sequence to a multi-set of words, and we're losing the information on the ordering of the words in the sentence. So we need to kind of encode this structure still in the model. So how do they do that? They use a positional encoding, which is a function of the word indexes, and these are sines and cosines of the word of the grid graph that is present. I mean, the grid graph is basically the sequence of the words in the sentence. So based on this motivation, it's natural to use a mechanism to encode node position in the sentence, but it's not straightforward because we don't have an ordering of the nodes in the graph. So what we do is we use Laplacian eigenvectors corresponding to the node as the node positional encoding, and we use in the similar fashion in graph transformers as it was used in the original transformer. And by definition, it naturally generalizes the sinusoidal positional encoding that was used in the original transformers, because the sinusoidal positional encoding can be interpreted as the eigenvectors of the grid graph. So this is the second key design aspect that we considered. And finally, we have a graph transformer with this architecture on the right. So if you see this, the middle architecture is the basic graph transformer layer that we developed. And trying to see with the original transformer encoder, we have the positional encoding replaced by the Laplacian eigenvectors. We have the multi-attention mechanism that only takes the local one-hop neighbors, and we have the respective feed-forward model. And we have another architecture on the right, which takes in the edge information. So I'll walk through each of these one by one. And corresponding to the original transformer, what are the differences in this architecture? I'll try to walk one by one. First, like I already said, the attention mechanism is a function of neighborhood connectivity. So it takes in all the edges, which are the one-hop neighbors for node, instead of taking all the other words in the sentence. So this is represented by the j belonging to neighbor of I. In case of transformer, it was j belonging to the s, which was the sentence set of all the other words. So yeah, so the first difference was that we use the attention only to the local neighbors. The second, the positional encoding mechanism, we use Laplacian eigenvectors of the nodes. The third, we replace the layer norm by batch norm, because in the case of graphs, when we deal with batches of variable graphs, each of the graphs can have a variable number of size. For example, in molecular training, a molecular graph can have 9 nodes or 10 nodes, and another graph can have 20, 25 nodes. So we have this batch of variable sizes, and in practice, batch norm was found to be better, and we replaced the layer norm with the batch norm. In the fourth difference is that we have an architecture that explicitly accounts the edge feature. For example, if we have a molecule where the edge represents single bond, double bond, and so on. So this edge feature here is used to encode that information, and it helps modify the implicit attention score and then update the actual attention scores when the feature is aggregated. So this architecture actually takes in account any available edge information that is present in the dataset. So this becomes the graph transformer finally, where we have all these capabilities, the positional encoding, the local attention, and also the edge information. And the edge information is used in the softmax attention function. So So yeah, this becomes the graph transform architecture, and it's basically the idea behind this architecture is to simply generalize the transformers to graphs. And the question that that was asked in Zoom, yeah, wouldn't global attention be useful? So the answer to this is again, in when we're doing sparse attention, we are trying to treat different neighbors differently, and this was not possible when we do full attention. When we use this architecture and when we use this full attention by replacing this local attention, the performance is not as good as the local attention. This is the reason why we resorted to using local attention in this case. And when we have large graphs, for example, a graph with 500 nodes, consider that the global attention would provide a n square complexity. So we would require a 500 cross 500 matrix to be maintained. In case of local neighbors attention, the complexity is proportional to the number of edges. So the number of edges in a real world graph is usually always lesser than, or always very lesser than the n square. So O of E is less than O of n squared. So it computationally becomes much efficient when we're trying to use local attention. And actually, to your question, very recently, now I'll come to this slide. To your question, like why not use full attention, because it would encode more information. Despite the challenges of complexity and the losing of rich structure, actually recently, several fully connected transformer GNNs have been proposed, and they are better only when powerful positional encoding are used. If powerful Ps are not used, they're not very better. So it can be seen that when fully connection is being used, it gets rid of the information that is coming in the form of the sparse structure. So the PE is something that helps the model to encode this structure information, and hence it performs better. So recently there are three different works that I highlight here. The first is the spectral attention that it performs full attention, and it's similar to a transform, but there are two key differences. First, it uses a learnable PE module, and which is a function on the eigenvalues and eigenvectors. It gives a fixed size positional encoding. And second, when they're doing the full attention, there are separate learnable parameters for the actual edges and for the existing edges. So these two differences actually helps the model to perform the full attention on the graph. Using simply the full attention is not very powerful, as we discovered in the previous work. Similarly, a next model, GraphET, it uses a distance-based positional encoding. After each attention computation, it uses this distance information to improve the attention score. And next is GraphArmor, which has a combination of centrality, spatial, and edge encoding. It uses this as node information, additional node information, and also to improve the attention score, which is the edge encoding part. So these three methods, they use fully connected global attention, and simply using fully connected global attention is not powerful, but they are powerful by the presence of the positional encoding. And in the case of spectral attention, also because of the fact that there are separate parameters for real and non-real edges. So now we move towards the end of this presentation. I think we would still have time. So I mean, we can discuss several aspects of the presentation, like after the conclusion. But towards the conclusion, I would like to highlight some of the. First of all, I'll recap of what we went through, and then I'll highlight some of the applications, challenges, and research trends in this field. So we saw that how the underlying geometry of data is important, and without it, the sample complexity of data that would be necessary for training a model would be very high, because on images, if we used MLP, we would require several instances of the shifted images in order for the model to learn the shift invariance. In the similar case of graphs, if we would not have GNNs, we would require several permutations of the same graph in order to learn the permutation invariance on the data. So we saw how this underlying geometry is important in order to develop and decide which architecture is good for which. And in the next session, in the afternoon session, Professor Michael Bronstein will specifically deal on this kind of thing, and he will present this principal framework. So the second, we saw that how convolution can be generalized from images to graphs, and it gives rise to this message passing mechanism. Then we saw what are the different uh, level tasks that can be predicted on the graphs that are at node level, edge level, and graph level. And then we discussed graph transformer, which is a general architecture to extend transformers on ordinary graphs, ordinary or any kind of graphs. And this is an active area of research. We still will see new kind of models developed in the coming few months of coming years. So now, after these discussions, let's see what are the applications, what are some real world applications that have already been done in the last 2 years, what are the challenges, and what are the future research trends. So I'll try to highlight some application which are already in production. So in 2021, in 2021, Google Maps had released a paper that showed that their current Google Maps application actually uses a message passing based model to learn different behaviors of the traffic. And it shows up to a 50% improvements in several cities of the world. So how it's done is it considers the snapshots of the places. For example, this is a road network. It divides into super segments, which are then considered as the nodes, and the neighbors are as shown. And to learn the feature at each node, it considers its neighbor information and different feature present at the particular super segment. So this is one of the very cool applications where it was shown that when we have a model that is explicitly based on the arbitrary graph structure, which is different for different cities of the world, and at different edges and nodes we have certain information, then we have a very powerful model that can predict estimated time arrival on Google Maps. So this is one of the very exciting applications. Second, in 2020, there was a antibiotic that was discovered, which exhibits some, which was discovered using a GNN based model. So basically what it did was it trained on a property that was important to be inhibited by a particular antibiotic. And based on a model that was learned on this kind of property, it searched through a big database to find the most candidate antibiotics that was later sent for experimental tests. And then finally, the molecule was discovered as the halicin. You can read about it. It's a very interesting application of deep learning that uses GNNs for antibiotic or drug discovery in general. And next, Uber Eats is a food delivery platform from the Uber, and it uses graph learning to recommend new food items to the users based on how the user has interacted on the platform and based on the past order, things like this. So these are also very complex information. So they can be represented in the terms of graphs. And with Uber Eats, they showed that they are actually getting good recommendation outputs by using graph learning. And finally, it's also used in social network applications. In 2019, Fabula AI, which is a startup of Professor Michael Bronstein and his collaborators. So they had a algorithm. They had trained a model that could detect fake news in Twitter graphs. So this is also very exciting application, and this was actually acquired by Twitter, and now they're working on several applications related to social network domain. So these are different application that shows how GNNs are actually very powerful, and there are actually several more also, but I just showed this to give an idea of where are ultimately these things being applied in the real world. There are several challenges and the current research trends in GNNs. So the first is understanding more about the expressivity of the graphs and improving the performance of travel models, because we saw that when we are using I'll tell in this part in the next session when we will discuss explicitly on the theory of GNNs. So this is one of the interesting areas where more study is being conducted to understand more nicely about different performance capabilities, limitations of GNNs. The second application is, or second challenges is to extend these GNNs to dynamic graphs where such as tweets or posts in social media which change at every time instant. Third, scaling these models to large sizes such as billions or trillions of nodes, and also performing relational graph inference for cases where we don't have any explicit relation information. And finally, trying to apply all these different GNNs into different application areas. So these are the focus areas that are currently people are working in this field, and also future research trends would emerge from works in these areas. So yeah, this is the final slide. I'll share this slide later, and they have very useful resources from which you can actually start. And I think it's a comprehensive list of different code libraries, tutorials, courses, and some of the data sets that you could use for trying to get a hands-on with graph neural networks. So thank you very much. I hope that was a useful introduction. And I mean, you can even ask the question by speaking as well, or you can chat, put in the chat any question if you have. Thank you very much.